Hello students, welcome to today's lecture on data structures. In our previous sessions, we have discussed about several types of sorting techniques, starting with insertion sort, selection sort, bubble sort, followed by merge sort and quick sort, which are based on divide and conquer algorithm. So if you observe all those previous sorting techniques, all of them are based on element comparisons. So sorting is done based on element comparisons and then moving the positions of elements based on the requirements. But there is another sorting technique, a special sorting technique available, which is not based on element comparisons, which is Radix Sort. This Radix Sort does not compare the elements, but it moves the elements into respective positions based on the radix of the corresponding number systems. Okay, so let us go through this radix sort now. This is probably the easiest sorting technique, but not that efficient for sorting purposes. There is an algorithm called as counting sort before the invention of this radix sort. First, you need to understand what is this counting sort, and then the problems with counting sort, then how these are overcome in radix sort algorithm. So in counting sort, to sort any given set of elements, any given list of elements, what you require is you require n number of buckets where n is the number of different elements in the given list. I repeat the algorithm. To sort n elements, in a given list, we need the number of buckets equal to the numbers which are distinct, or the number of distinct elements in the list. For example, in this we have 8, 5, 1, 5, 9, 5, 6, 2, 7. So if you count the number of distinct elements, 1, 2, 3, this is repeated, 4, repeated, 5, 6, 7 elements. So there are 7 elements. So you require 7 positions or 7 buckets to store these elements. And then because there are such number of buckets equal to the numbers here, distinct elements here, each bucket can contain one element, or else you can choose any number of buckets which is equal to the largest number in the corresponding list. What is the largest number here? 9. So you can go with 9 buckets also, which is also possible. So you can choose highest number in the list and create that many number of buckets and put every element inside that individual bucket based on the corresponding element. So 8 is put into 8th bucket, 5 is put into 5th bucket, 1 is put into first bucket, and then 5 is put into 5th bucket again. There are multiple elements, and 9 is put into 9th bucket, 5 is again put into the 5th bucket, 6 is put into 6th bucket, 2 is put into 2nd bucket, 7 is put into 7th bucket. So we just move the elements into the respective buckets based on the value in the list. Okay, and then just write down or take them out from the buckets from left to right. So you will get 1, 2, 5, 5, 5, 6, 7, 8, 9, which is nothing but the sorted order. It looks very simple, but if you observe the difficulty in this, for example, the maximum number in the corresponding list is infinity. Let us say the maximum number in the uh, list is infinity. So how many buckets you require? The unlimited space. You require unlimited space to store the elements into the corresponding buckets. And another problem is, even if you reserve that memory, another problem is, let us say there are only 4 elements, one of them is positive infinity. So what happens? The reservation is infinite number of memory locations, but out of all those infinite number of memory locations, you will be using only 4 locations. 4 buckets will be used. the remaining amount of memory is wasted, right? So that is the difficulty with this counting sort technique, which is overcome by the Radix sort algorithm. So in Radix sort algorithm, I think all of you know what is meant by Radix. Radix is nothing but the base. It represents the base of a particular number system. So Radix sort works based on the radix of the corresponding number system. For example, in binary number system, the base is 2, and in octal number system, the base is 8. In decimal number system, the base is 10. In hexadecimal number system, the base is 16. So based on the radix, the algorithm works. Okay, let us understand how it works. Suppose if you consider any integer which we want to store into uh, a sorting order, integer can be viewed like this: a collection of digits, d1, d2, so on, dk. Let us say there are k digits in a particular integer. In that, we treat this d1 as the most significant digit. That means its positional value is high, and dk is the least significant digit. That means its positional value is least. For example, in any decimal number system, let us say 497 is the integer, then the positional value of this 7 is going to be 10 power 0, and this is 10 power 1, this is 10 power 2. This number will be equal to 7 into 10 power 0 plus 9 into 10 power 1 plus 4 into 10 square. So that is what the number is, 497. Therefore, because this is in 100th position, 4 is the most significant digit, representing 400 actually. This digit is 4, even though 4, but its position makes it as 400. And this is 9, and its position makes it as 90. And this is 7, its position makes it as 7. So this is the least significant digit, this is the next least significant digit, and this is the most significant digit. So you can treat any number like this, you can view any number like this, any integer like this. Okay, so d1 is the most significant digit, and dk is the least significant digit. Okay, so now after viewing an integer like this, how Radix sort works? The algorithm says like this: sort by the least significant digit first. So we need to consider the least significant digit first, and then apply counting sort on it. That means consider all the least significant digits of the numbers in the list, and then put them into the buckets, respective buckets, based on counting sort. So how many buckets are required? It depends on the corresponding radix. For example, if you are sorting decimal numbers, radix is 10. That is base is 10. Decimal number system has a base 10, and the digits are 0 to 9. Okay. Therefore, how many buckets are required for sorting decimal numbers? You need 10 buckets: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you are using Radix Sort for sorting numbers in hexadecimal number system, then how many buckets will be required? What is the base of hexadecimal number system? 16. So you require 16 buckets starting from 0 to 15. Okay, so number of buckets required by this algorithm depends on the number system on which this sorting algorithm is applied. So if you are applying it on decimal number system, then you require 10 buckets representing each digit of the decimal number system. Okay, so that is what the first step is. So we'll consider the least significant digit first, and we put that number based on the least significant digit into the respective bucket. Okay, buckets are also called as bins, and then continue the same process by retrieving the numbers from bin 0, bin 1, and so on, bin 2, by ordering them in the order of bin 0, bin 1, so on, bin 9, uh, producing the intermediate list. It's not the sorted list, it is the intermediate list produced by the previous step. And then we consider that as input for the next step. The next step is Consider the next least significant digit again and do the same process. Apply counting sort, put that elements into the bins again. Okay, so we'll continue this process until all the numbers have been sorted and all k digits. Okay, now let us understand this with an example. This is not a difficult algorithm to understand. Say there are 1, 2, 3, 4, 5, 6, 7, 8 elements are there. If you observe this list of elements, the maximum element is 677, which contains 3 digits, and every number in this list must be made as 3-digit numbers. So if you observe, 61 is having only 2 digits, therefore we precede a 0 before 61. Okay, and also 87 contains only 2 digits, therefore we keep a 0 before 87, making it a 3-digit number. So the number of digits in every number in the list must be equal. Okay, so for this what you need to do is just look at the highest number in the list, how many digits are there in the corresponding highest number, and make all the numbers in the list such a way that the number of digits is equal to highest number. Okay, so because 677 is having 3 digits, all the numbers in the list must be made as 3-digit numbers. Okay, if required, you can push some zeros before the number if required. Otherwise, there is no need. Okay. Now let us understand the first pass. The first pass is, what is it? Based on the least significant digit, we move the corresponding numbers into the respective bins. Okay, so what is the first number here? 275. What is the least significant in this? 5. So 275 will be moved into the bin 5. What is bin 5? This one. So 275 is moved into this bin. Okay, then 087, 87. What is the least significant digit here? 7. So this number will be moved into 7. So that is 87 here. Then 426. What is the least significant digit? 6 it is. So 426 will be moved to bin 6. Bin 6, this one, 426. And so on. 061. Least significant digit is 1. So it is moved to bin 1, 61. 509 is moved to bin 9. So bin 9. 170 is moved to bin 0. This one. 677 is moved to bin 7. This one. There is already one number, and you insert it again after that number, 087, and followed by that 677. And the last number is 503. Digit least significant digit is 3. So move this number to bin 3. Where is it? This one, 503. And then after performing this operation, take out all these numbers from starting from bin 0 moving towards bin 9 in the same order. Okay, so 170, 061, 503, 275, 426, 087, 677. Two numbers are there in this bin, so both of them in the same order in which they are kept will be taken out. So 87, 677, and the last number is 509 in bin 9. So this is the output from pass 1, first pass. So this is the actual list of elements to be sorted, and we got this list after the first pass, and this will be considered for second pass to apply the same process again. This time we consider digit 2, least significant digit 2. What is that least significant digit 2? This is completed. Least significant digit 1 is completed. So we start from this number, second digit from right. Okay, so 7. So 170 is moved to 7th bin, this one here. 061, 6. So 061 is moved to bin 6. 503 is moved to 0th bin, because second digit is 0. It is moved to 503 here, 0th bin. 275 is moved to 7th bin here. 426 is moved to second bin. 087 is moved to 8th bin. This one, 8th bin. 677 is moved to 7th bin. The second digit is 7. Therefore, 677. Already there are two elements, so this is third element in 7th bin. And 509 is moved to 0th bin. There are two elements now in 0th. Again, we take out these numbers in the order. What is that order? 503, 509, 426, 061, 170, 275, 677, 087. That is the list of elements. So if you observe, this is it. 503, 509, 426, 061, 170, 275, 677, 087. So we take out all the numbers in the same order from 0th bin to 9th bin. Okay. In third pass, now if you observe, what is remaining? The most significant digit. So we start with most significant digit and we put all the numbers into the respective bins. So 503 is the first number, which is the output from second pass. So 503 is kept into fifth bin. Why? Because most significant digit is 5. So 503 is kept in bin 5. 509, again it is 5. So bin 5. 426, bin 4. 061, bin 0. 170, bin 1. 275, bin 2. 677, bin 6. 087, 0, bin 0. And take out the numbers 061, 087, 170, 275, 426, 503, 509, 677. If you observe, that is the sorted order of the given list, right? So that is how it works. Okay. What is the algorithm here? What it is saying? Again, we'll go back to the algorithm steps. What is that algorithm? We consider the least significant digit first, and then we put all the numbers into the corresponding bins based on this least significant digit. And then we take out all those numbers from starting from bin 0 to bin 9 or last bin in the same order. Okay, that will become output of the first pass, which is an input to the second pass. Again, we perform the same step with the next least significant digit, and we continue the process until all the digits are completed. So if there are k digits in the numbers of a list, you require k passes. Okay, so that is what it is. The algorithm is. Does it really work? Yes, we saw the example, because it is clearly based on the significant digits. When it is sorted on the most significant digit, obviously the bins will contain the sorted list only. Okay, so it works. But then what are the problems and what is the time complexity of this algorithm? The time complexity of algorithm depends, majorly depends on the base of the corresponding number system. If the base R decreases, then the number of passes uh, increases, right? Increasing the base R will decrease the number of pass. This is mutually opposite. If you increase the base R, the number of passes will be decreased. If you decrease the base R, that is number of passes gets increased. Okay. Let us identify the time complexity of Radix Sort algorithm. How many passes are required? Assuming that there are k digits in the numbers, you require k passes to perform the sorting, right? And how much time is required in each pass? Each pass, if you observe, you need to insert n elements into the respective bins, and then take out all the n numbers after placing the elements into bins. So two operations. N elements are kept inside the array and n elements are taken out of the array. So how many operations are performed there? 2n plus n operations. Okay, one n operations for insertion, n operations for outing. So taking out. So 2n operations are required. So each pass requires 2n operations. Therefore, there are k passes required, and each pass requires 2n time. The total time complexity is big O of 2nk. Assuming that 2 and k are constant, the time complexity is going to be big O of n. Okay, so the time complexity of Radix Sort is big O of n. But then what is the difficulty of Radix Sort? It is very difficult to implement the buckets, because let us say if you have in a very large number which contains, let us say, mm, uh, infinite, a positive infinite, then how many passes are required? Infinite number of passes are required. So again, the same problem is there. Therefore, this even though the list contains only few elements, let us say three elements are there. Assume the situation, only three elements are there, and one of these three elements is a very big number containing 15 digits. How many passes are required? You require 15 passes, right? So that is the difficulty with Radix Sort. The problem with Radix Sort is it will not consider any element-based comparisons. Therefore, in special cases, Radix Sort will not work. Okay, so that is the problem. But still, you can use this algorithm whenever there are numbers, evenly distributed numbers available uh, in a particular list, right? So that's all about the Radix Sort algorithm, and we have completed the first unit with this. When we come back, we will start the second unit, which is nothing but a linked list concept, which is very important for us because to implement the mm, third unit, fourth unit, fifth unit, you need the knowledge of linked list and you need implementation of linked list in a proper way. Therefore, that will be the second unit will be crucial for you. You need to understand it properly. We'll spend more time for understanding that second unit. Thank you for now. See you again in our next session.